It's time for another specials video. It's going to be a bit different than the previous one because in that one, I talked about infinite arithmetic series and I proved something to be true, even though it seemed a bit controversial at first. It was technically true because the proof was all correct. In this video, however, I'm going to prove something to be true, but it's not actually true. That's because there's one small flaw in the proof, very tiny and hard to spot. So if you can spot it, let me know in the comments below. Even if you can't, I'll explain the flaw at the end of the video after my proof. But today I'm going to prove that all triangles are equilateral. And technically I'm not actually going to prove it. It's a proof for that, but it's a false proof. So that statement isn't actually true, but I'm going to show you proof that it is true, and then I'm going to explain the flaw in it later. Okay, with that out of the way, let's draw a triangle. I'm going to use different colors for this one. So I'm starting off with a pink triangle. And this doesn't look very equilateral, does it? I'm going to prove that it is. We're going to start off by drawing a perpendicular bisector to this side. A perpendicular bisector is basically a line that is perpendicular or makes a right angle with one of the sides and divides it exactly in half. I'm going to extend this a bit longer. And after that, I'm also going to draw an angle bisector of this angle. It divides it exactly into two congruent angles, and they intersect at this point. Now, a little note, a little disclaimer, I suppose. Proper form is to draw a different number of tick marks on different congruent sides. For example, if I had these two sides, I would draw one tick mark on them. And then if I have these two different sides, they're different than the first two, I would draw two tick marks on them to show that these two are congruent but not congruent to these. Well, since I'm going to have to draw a lot of congruent things, so I might need even 6 tick marks on one, and also this is just a specials proof, not an actual geometry lesson. I'm just going to use different colors to show different congruencies. Okay, with that out of the way, what can we do with this? Well, we can draw the perpendicular line from this point to the other sides. What does this do? Well, let's take these triangles out here. So, can we prove that these two triangles are congruent? We actually have everything we need. We have right angles, and that automatically means that these angles are congruent. We have congruent angles because of the angle bisector. It creates two congruent angles. So we have two congruent angles right now, two pairs of congruent angles, and then we know that this side is congruent to this side because in the actual diagram, it's itself. Both of the sides are the same exact thing. I just separated them here so it's easier to see. But it means that these two are congruent. So now we have AAS, angle, angle, side, and that's a valid congruency theorem, meaning we have congruence between these two triangles. What can we do with it? Well, there's something called CPCTC, and that states that corresponding parts of congruent triangles are congruent. Each letter stands for a word in that phrase. So we know these two triangles are congruent. We can find the corresponding parts of them now to make use of it. Well, we know that this is congruent to this because they're corresponding sides, and we know that this is congruent to this because they're corresponding sides. I'm using two tick marks for these because they're the same exact color, so better not to get confused with them. Okay, now that we've done that, I'm going to continue on with our proof. We'll use a different color, and we can draw the segment from this point to the other vertices. So now we created 4 more triangles in effect. I'm going to take a look at these triangles first instead of the middle ones. So again, I'll draw them outside so it's easier to see. We know that they're right angles. That's given because it's a perpendicular bisector. The second part of that word, perpendicular bisector, means that these two are the exact same. And now we just need one more thing. And that thing comes similar to the previous one. We know that this is congruent to this because they're the same exact segment in the diagram. So we have SAS, yet another valid congruency theorem. So now we know another pair of congruent triangles, and we can use CPCTC again. Now we know that this is congruent to this because that is those are corresponding sides, and we use CPCTC to find out that they're congruent. The last pair of triangles that we need to prove, I'll use a different color for, again. It's this one. These two triangles. Let's take them out for further inspection. We have this one right here, and we have this one right here. So this one, we know that they're right angles. We know that these two sides are congruent because that's given from the first pair of congruent triangles, and the second pair of congruent triangles gives us that these are. So now we can see that it's a side, side, and an angle. But if you remember from geometry, this is not a valid congruency theorem. Note that this is not the flaw in the proof because I'm explaining it right now. Instead, these two triangles are actually congruent because it's a right triangle, and SSA works for only right triangles. It's a theorem called hypotenuse leg. If you have a hypotenuse and a leg of a right triangle that is congruent to the corresponding ones of another right triangle, they are congruent. It's a special case of SSA that works. Other cases of SSA do not work, so this is not the flaw. Keep watching. We know that these two are now congruent because hypotenuse leg. Now that we have all this, we can use CPCTC one last time. We can use it on this third pair of congruent triangles and say that this is congruent to this. And that is because CPCTC, we know these two triangles are congruent, so these are the corresponding sides. So let's label this segment 1 right here from the first pair. That means this is also 1 because it's congruent. Similarly, if this is 2, this is also 2 because they're congruent. So in effect, we have 1 plus 2 is equal to 1 plus 2 because since they're made up of the same numbers, they are equal. So we're basically proving that these two sides, let me use letters so it's easier to see. We're basically saying that side length of AB is equal to side length of AC, which means that AB is congruent to AC. And we can prove this because we know that they're made up of two congruent parts. We can use the postulate that says that where if we have two segments that are the same and they're collinear, we can find the sum of them both because they're just the sum of each individual part. And we know the individual parts are congruent, which means that the sum is congruent. So we have AB is congruent to AC. And that means that two of the sides are congruent. But we can shift this triangle. We can draw the perpendicular bisector to a different side and make the proof for a different side, which basically means that AB is congruent to BC and AC is congruent to CB. So in effect, all three sides are congruent to each other. We can just use the proof on a different side and identify the other two sides that are congruent to each other, which means all three sides are congruent, which means the triangle is equilateral. Hence the proof, the triangle is equilateral. All triangles are equilateral because we didn't make any specific thing like this is a scalene triangle or this is an acute triangle. We said that all triangles are equilateral because this is a generalized triangle. Now what's the flaw? Because there is a flaw, and that's the thing that I'm going to explain right now. The thing is, when we first started the proof, we used a triangle, we drew the perpendicular bisector, and the thing is, we drew the angle bisector inaccurately. Even though it's a little bit inaccurate, as you can see, these angles are not actually equal to each other. Even though it was a little bit inaccurate, it changed the entire thing, because actually the angle bisector is supposed to intersect the perpendicular bisector outside of the triangle. And now when we create these triangles, we see that we don't know anything about these side lengths AB and AC. All we know is that these outside side lengths are congruent, but that doesn't help us. All we want to is AB and AC, not these outside. So the entire proof is messed up because we drew the angle bisector inside. The intersection point is not supposed to be inside, and that was the flaw. That was the major flaw in this proof. Like I said, it was very hard to see, But yes, it messed up the entire proof and we got something insane. That's why I called it insane geometric proof. Now, you might be thinking, is that true for all triangles then? The angle bisector always intersects the perpendicular bisector outside the triangle, except for equilateral triangles? Yes, that's true. The only time that the angle bisector intersects the perpendicular bisector inside the triangle is in an equilateral triangle. And the funny thing is, they are the same exact segments, so obviously they intersect. If you have an equilateral or even an isosceles triangle, these two intersect each other because they're the same exact length. So that's how we proved that all triangles are equilateral, but it wasn't really proof because it was false. Proof, quote unquote. And that one flaw changed the entire proof. So I hope you like this video. If you like proofs like this, either similar to the first special or this special, let me know and I'll make more videos like this, more specials that seem interesting. And as always, let me know if you have any helpful suggestions or anything I should improve on. See you in our next video.